Thanks. Hi, everyone. Everyone, can you hear me? Well, if you can't hear me, just stay in chat. I just assume that everyone hears me. Okay. Welcome to Lab 11 on Transformers and Large Language Models. Let's get started. First, I want to take a quick recap of the attention mechanism. So, compared to a standard sequence model, instead of depending wholly on solely on a hidden state, we're going to calculate for each output hidden output state, and each hidden state for input we calculate some kind of a coefficient, and then we time that coefficient with their hidden state to take a weighted average as information supplied to each output, and this is called attention. Yes. And we have an updated version of the attention where instead of calculating the weights directly from their hidden states, we are going to pass this through some module to get a key and vectors for each of the hidden states in the input, and a query hidden vector for each of the states in output. And when we want to calculate the weights, we take the inner product of the Q and K's to get a weight between a output and all of the inputs, and then we use the weight as the coefficient and multiplies it with the values to get the usual weighted average of the hidden states. Yes. And self-attention is when you are having a sequence, you only have one sequence, and a way to apply attention is to take the input sequence as the sequence and the output sequence also as this sequence. So you're picking every token or every stuff in the sequence, and you're calculating the weights between each pair. So each hidden state here now has to generate all the three vectors Q, K, and V, and then you're going to calculate the coefficients and the weights in the usual way. So let's look at it. This example shows the case where in the output you're calculating the attention between all the inputs and the output. And if you look at this, like this Q has to be multiplied with all of the K's. So as an analogy, it is a case where you have another sequence, and it's exactly the same as this one, but you're calculating the values for the first entry. So if you look at this again, right, you take the Q of the first or zeros hidden state, it's dot product with all the keys for all of them. And
Can you speak more into the microphone? They're saying they're having trouble.
Oh. Okay. All right. Is it better? Okay. Well, I hope it's better. Oh, I have to bring it really close. Okay. Yeah. Sure. Sorry. Yeah. So self-attention is just you take your input and you calculate the weight by dot product in your Q with all the K's, and after you get this set of weights, you take the weighted average or weighted sum of everyone's V vector. That's self-attention. And multi-head self-attention is basically when you are doing this stuff, you split your H0 or H1, H2, H3, H4 into like several little segments, and each of them can have a different Q, K, and V, and you do the same set of calculations for each set of segments, and then after you arrive at this hidden state here, you just concatenate them back, and there's definitely some apparent advantages. One of the advantages is that when you calculate the attention, everything boils down to a square matrix here of coefficients, and no matter how large the dimension you have, you're always going to arrive at a single attention map, which gets multiplied with the V vectors. And if you are breaking them up into smaller segments or multiple heads, in this case, you are allowed to have several different attention maps that will be allowing your model to kind of recognize different patterns or look at intuitively looking at different places in your input. This is very helpful. Yes. And later we have mask self-attention. Imagine a case in your output sequence. So suppose that this is the thing that your model is going to generate. And what is going to happen at test time is that because you're going to do something called autoregressive generation, which means that you're going to generate one by one from start to end. There's some tokens that has to be generated first, some tokens that have to be generated late, and apparently the tokens that is generated first should not learn information about what is going to be generated next. And this is what's going to be happen in the test in the inference time. So in order to make your model perform well, you ideally want to let your model experience the same thing during training. And the way we do this is by applying this so-called causal mask. It basically just maybe converts your attention matrix into a lower triangular one. So if you look at this one, this matrix here, each row corresponds to the Qs and Ks, but because you do not want the tokens in the front of sequences know anything about the tokens after it, you should just convert, like forcefully make the attention weights for every token after your current token to be zero. So when you do this weighted average across the V vectors, it is equivalent to not seeing them. So that's basically the idea. And let's finally get to this famous paper. I think it's published in 2017 by Google. So this is a model that only uses attention mechanism, no recurrent network stuff, and achieves decent performance on a wide range of tasks. And the key to this is actually how to scale it up. Like I think many people have tried to do this, but they did not really have a great improving performance compared to conventional recurrent networks because they just did not scale it up. It's like not enough training, not enough number of parameters. But this is a very important model regardless. Everyone's using transformers now for any form of data that can be converted into a sequence in some way. So let's look at what happens. And the first starting component is these inputs and outputs. If you think about the case where in homework 3, like you're trying to decode characters, right? But in the case of the transformer, what really happens is that people does not break the words into characters, but they break them into something called tokens. It's like a substructure of words. It's like a token is a unit that is smaller than words, but larger than characters. And if you look at this example here, you can see that some of the words are it itself as a whole is a token. For example, learning or this comprehensive. And other ones are can be broken into several tokens. Okay, I'm not seeing such an example here. Oh, this conventional here. It itself is a word, but it is broken into convention and all, which it makes sense because this AL can be paired with a lot of words. So this tokenizer just decides. A tokenizer is like a dictionary. And the tokenizer just decides to break this into a separate token, and each of them is assigned an index, pretty similar to the it's like vocab map or something. Your homework 3. For each string, you're gonna convert them into an index for a model to predict. If you recall the classification task in your previous homeworks, right? You have a lot of classes. It's a similar idea here. Each token is a kind of like something like a class, and you want to predict them, so you want to assign them an index. That's basically what happens. And next we jump to embeddings. I think we have also seen embeddings this term in your homeworks. And what happens is that it basically stores. So it's like for each token, right? We have an index for each token, and for each index we store a representation for the token, and it does not have any relationship with the index. So it is just actually a array that stores stuff, and you can get the value by supplying it to the index, and it can be imagined to something similar as a linear layer if you design the indices smartly by this example. But overall, it's like if you think of it as an array, it starts to make a lot of sense. So yeah, this is basically what embedding does. And we have positional encoding. And the reason we need positional encoding is that if you think of the attention mechanism, that is not without the recurrent structure. What happens is that you're just taking pairwise dot product of the sum vectors to get weights and take weighted average. And if you switch the order of, say, the input sequence, if you switch the order of the two stuff, the attention mechanism gives the same result, because if you think of it, right, even if two stuff is like swapped, because the attention is only calculating, like taking pairs, calculating a dot product, taking this scatter and multiply with another vector, it does not actually incorporate the order as an information to the attention calculation. So this is gonna cause a lot of problems, because in some tasks, actually most tasks, in most sequence tasks, like order means a lot. So if you're gonna do machine translation, or like the ASR task, like the speech to language task you've been doing for homework 3, orders really matters, right? It doesn't make sense to just drop this information. So the way we do this is that we add some value that hopefully incorporates the information of the location of the token in the sequence. And in their paper, they use this stuff, some sinusoidal function. This basically means that for each position, which is the first index here, and for each dimension, which is the second index here. So the dimension is just that, like for all the homeworks you've been doing, you have something, you mostly have a dimension as either the number of channels for CNN layers, or like the number of dimensions for LSTM layers, something like that. So you have some dimension here, and for the even dimensions, you calculate this. For all dimensions, you calculate this. And the reason that the authors have chosen these set of weird functions is that they claimed, well, if we have a fixed offset of k, then these values at position plus k can be expressed as a linear combination of the previous embeddings. Like I asked ChatGPT, I don't know how to solve the math. ChatGPT told me it is because of this, and I think it makes sense. If you see, this is like, a linear combination of the previous embeddings. So given this, they're hoping that the model can learn, like because of the linear combination, hopefully the model will learn something about the location information, which definitely makes sense. And another kind of positional encoding, which is a simpler way kind of in positional encoding, it's just that it initializes another set of embeddings, like the embedding we had for the tokens. But in order to do that, you have to take fixed size inputs, or at least have an upper bound of the input size. There's definitely cases of that satisfy such conditions. We will look at it later. But just keep in mind that in this case, in this paper, because they are taking a sequence of variable length, they just designed this kind of math, kind of weird equations. Yes. And now let's move the rest of the architectures. So this part of the model is called the encoders, which take the input sequence. It converts the tokens into embeddings, applies positional encoding, and then arrives at multi-height attention stuff we discussed earlier. And what goes out of this module is like an updated hidden vector corresponding to each token in your sequence. And you do some normalization, you add a skip connection, it passes through a feed-forward layer, and you do another normalization and feed-forward skip connection. And this together, like these 4 processes, is an encoder block. And you can like stack multiple encoder blocks, like however you want, unless as long as you have the computational resource, like stack a lot of them. That is called an encoder. So what comes into the encoder is input embeddings, plus there is the positional encoding, and what comes out is a sequence of exactly the same size, but with information that at each token it learns mixed information of all other tokens in the sequence. Okay, now let's look at the decoder. The decoder is a bit more complicated. So firstly, what is the same is that it takes the output sequence, pass converted to embeddings, and plus positional encodings. And then it arrives at a mask multi-head attention, and we explained why there's a mask here. This is the output. So okay, in inference time, when we're generating stuff, what is going to happen is that it passed what is called a start of sentence as the only output sequence. And I think you understand what start of sentence is if you have, because today homework 3 part 2 is going to do. So yeah, it passes the start of sentence, and then it goes through all this stuff, right? And it arrives at the output probabilities, which is a probability across the vocabulary, across all the tokens. And because in general, this probability gives you one token with the most probability. You just pick it as your result, which becomes the next sequence, next token in your generated sequence, and you make it input it back. You append it to your input output sequence. You pass it all the way back here again. You get another distribution across the vocabulary. You pick the most likely token and append it and append it, do it until you arrive at end of sentence. And I think you most likely understand what end of sentence is, and that's when you're gonna end, right? So, and this is what this is using the transformer to generate a sequence in a greedy way. And this is what is going to happen in inference. I'm saying this because I think it might help you a bit to understand what we are doing in training time in the output decoder. So given that in mind, what we're going to do in training is that we pass the entire ground truth output sequence here through this masked multi-head attention. And because in the generation process that I just described, we're doing tokens one by one, right? So it will never see journey starts with one step in the inference time, in actual time when you're generating stuff with the model. So you have to mask it out during training time to make sure that it does not learn to extract information from the stuff that's behind it. This is the reason we have masked multi-head attention, and we have the Euro skip connection and normalization. And then there's a cross attention stuff where the output sequence only supplies the Q vectors, and the input sequence supplies the K and V vectors. And if you think of the attention, what it's doing, it takes, for each output token, it calculates a weight with each input token and take a weighted average with respect to the weights on the hidden, like the V vectors of the input sequence. Like this is what multi-head attention does. So intuitively, you can think of it as the output tokens, the output sequence want to mix their information themselves, and then they are gonna grab some information from the input sequence, which makes a lot of sense, right? Because you have to like pass the information of the input sequence to the output sequence in some way. And the way it is being done here is through this multi-head cross-attention module. And after that, you have the free-forward connection, you have the normalization, and this is the classifier head, which generates the prediction across the vocabulary, and that's basically it. And I want to maybe expand a bit on how you want to train it. So as I just mentioned, what we're gonna do in the training time is that you pass all the input sequence here, all the output sequence in the decoder, and so if you think of this, at this point, this entire blocks of two attentions that are stacked n times, what get out of it is a sequence exactly the same shape as this output, but they have information mixed with the input sequence and with itself with this causal mask. So say if you have n tokens and embedding size of m, you're gonna get an output sequence of n times m vectors. And after you pass it through the linear layer, you're gonna have n times distribution across the vocabulary, which means that for each output sequence, each token in the output sequence, you predicted a distribution which is supposed to predict the next token in a sequence. So this is, after all, it becomes a big classification task, right? In each sample, where the difference with most of the classification tasks that you have done is that it classifies multiple stuffs in one sample, whereas in your homework 1 or homework 2, each sample have just one classification task in it. So I think if this might give a more intuitive understanding of what happens in the training process. Another thing to mention is teacher forcing. Teacher forcing means that when we are training our model, we are not letting it doing closed loop generation, but rather we are enforcing it to use the correct output when generating correct previous outputs when generating one output. So which means that in this case, when we are wanting it to predict like width, instead of letting it generate all the way to the first token itself, we're going to supply the first 3 tokens and let it predict width because the first 3 tokens we know is always correct. And I think there are apparently some benefits of doing teacher forcing. One of it is that it makes your training more stable. Because if you do closed loop generation, which means that you're gonna let your code model generate everything blindly, and then you're gonna apply the cross entropy loss, because it is after all a classification task. The error is gonna cascade a lot, and that's gonna it is likely to make your loss like explode quickly, and doing teacher forcing kinds of mitigates that. And another reason to mention it is the way the architecture is designed applies teacher forcing automatically, right? Because if you think of this, like the output sequence is being passed here, and the output sequence, the ground truth output sequence, and if you think of the what the attention stuffs do, it always has to take the ground truth answer to generate the predictions. And yeah, last thing to keep in mind, it's a classification task, nothing fancy. When I first self-learned this, I was kind of struggling with it a bit. But what you have to keep in mind is that it's a classification task. Nothing complicated, yes.
Okay, so now we'll move on to the second part where we'll basically introduce the basics of LLMs. So I believe in the guest lecture on Wednesday, the guest speaker kind of talked about some of his research on compound AI systems. So today we'll just go over some basics. So in the original Attention is All You Need paper in 2017, they presented the encoder-decoder structure, but in reality, there's like really 3 kinds of structures for language models. The first one is encoder only. The second one is the standard encoder-decoder one. And the third one is decoder only. So for the encoder only version, there are some representative models like BERT and its variants. And for encoder only LLMs, its nature is like non-autoregressive, which means that you don't need to like generate tokens one by one because that's not their inherent task. For encoder only language models, it's usually like used for tasks on like sentiment analysis where you're focusing on like understanding the sequence. And for encoder decoder models, which is the ones that the authors of the original paper proposed, it's kind of more flexible, so it can capture like the information in the original sequence and also to like generate new information using the decoder. But then in reality, like models today are actually mostly decoder only, including like GPT and Llama, which we'll talk about later. That's because like in reality, what we want for language models to do is to actually generate text. So to generate text, the nature of decoder only and its autoregressive nature like makes it more suitable for tasks like text generation, as we're essentially only trying to like predict the next token based on whatever previous sequence that we have. So large language models today, they are based on transformers, and then because of the scaling law that is, well, essentially everywhere in deep learning, we can basically just kind of escalate the size of our model. So if you take a look at the this graph that I believe it's like not comprehensive, but you can like see how these models have like escalated to hundreds of billions of parameters. Like for homeworks that we train, we usually like you would know like a model of 20 million would take you something like 10 or 20 minutes per epoch on your GPU. But then if you want to train like a model of hundreds of billions, it will probably need like thousands of the best GPUs like A100s to train for several months. So yeah, that's just little cap of the actual scale of the large language models that are actually, large. Okay, so the first model that we'll take a brief look at is T5. So T5 is a encoder decoder model. Um, the decoding strategy you've already implemented in 3P1 is beam search. So there are like different decoding strategies for language models because essentially you're trying to like sample a next token from a probability distribution. The naive way is of course just the greedy sampling. So you're taking just the argmax of that probability distribution. And then beam search would like give you a sequence of like a best or like a most probable sequence within some length. And then there's also things like top P sampling or nucleus sampling, which you will probably learn for homework 4. And then the model size for T5, the base is actually only 220 million parameters. But then there are also like variants of 3B and 11B, B standing for billion parameters, which are a lot larger and perform better on various tasks. And then another like popular large language model that we use today is Llama. I believe it is now already Llama 3.1 or 3.2 at the moment. So it is a decoder only model, and from the original paper, it has like mostly 3 improvements. The first one is it uses pre-normalization instead of kind of post-normalization. And then the second one is that they replace the standard relu activation with this Swiglu activation. And then the third one is that instead of using the original positional encoding that is actually a absolute position positional encoding, it uses like this rotary embeddings, which is a relative positional encoding, and I'll elaborate on that later. So let's first take a look at the difference of pre-norm and post-norm. I believe this was covered in Monday's lecture, but here is just a quick recap. So pre-norm would mean that you would take the layer norm and then split it into the phi4 layer and the residual connection. And then post-norm is basically your like you're not taking the layer norm on the residual connection. And then if you remember from Monday's lecture, you'll know that pre-norm is more stable in training, but then post-norm gives you kind of a better overall performance while it's like a bit harder to train. And the second improvement is the replacement of the the activation function. So for Llama, they use like the switch activation function. The formulas are provided here, and then this is probably just a experiment results that they found, which works better for training and performance. And the last one is how they changed the positional encodings of the transformer model. So we now know that the positional encoding is essentially very important in transformer models because self-attention is position invariant. So basically, you can like have a different sequence and mess up the order, and then it wouldn't really matter for the like the attention weights because they will still stay the same. So for the transformer model to actually learn like the positional information of your sequence, you would need a positional encoding. And the advantage of rotary embedding than the original positional encoding is that it would like it will focus on the relative distance between tokens or between like different positions of your sequence, which is more reasonable as like we want like the words near the word that you're like currently looking at to be kind of more important. And that's the intuition of like switching from the absolute positional encoding to a relative positional encoding like rope. You can read that the original paper if you're interested. And then last, I want to like briefly talk about like the research questions on LLMs. The first one is like efficiency of LLM inference. You can read relevant papers like VLM or paged attention. And then there's also like algorithms like speculative decoding to accelerate LLM inference. And then the second one is how to make LLMs multimodal. I believe we all use GPT, so you know that GPT 4.0 supports you to like input images as the input. And then we want to make like these LLMs actually be able to take all kinds of information, and then for now it would only generate text, but we want like a kind of a world model in the end, so it will can be like any form of input to any form of output. And today we'll touch a little bit on vision LMs later, which uses a vision encoder to encode information from images. And then last, there's also like the area of long context and better reasoning. And one of the most prevalent results on this is chain of thought, which we believe that the O1 model from OpenAI is using. So it would use like more complicated prompts to kind of enhance the reasoning of your language model inference. And yeah, that's pretty much it for all the things that we want to cover for the recap and a little the recap section. And then now we'll go through two notebooks, one for language task and one for like a multimodal vision language task.
Great. I hope the link's working. I updated last night, I didn't check. Oh, yes, that's good.
Can people see the Colab notebook? I'll assume yes. Okay.
Okay, we're gonna include two notebooks. So the first one is about the language, and the second one about the vision. So I'm gonna talk about the language first. Okay, so okay, like before we start talking about the model, we first need to do the pre-processing of the data set. So in the language task, for example, we do the translation, like translate from English to German. We need to process the we need to process the English sentences and the German sentences, which is to do the tokenization. Doing the tokenization is to put the sentence into pieces and then transfer these pieces to the numerical data, and then put them into the model. So there are lots of different ways to do the tokenization, which is there are lots of ways how we split the sentences. It is not necessarily like we need to split the sentences in by the words, but there are lots of different ways to split the sentences. After we have the tokens, we can start talking about the model architecture. So I think we have talked a lot about like what the model architecture looks like. So I can quickly go through this code. So so there are 4 basic blocks: the positional encoding, the multi-head self-attention, add and norm, and also feed-forward block. So for the first one, positional encoding. Positional encoding is to add the positional information to the input. So here we can see that this is the implementation of the positional encoding, which is just to follow the formula on the paper. And then this is a positional encoding. We need to put those information added to the input and then add a dropout layer after that. Second, for the multi-head self-attention, we're gonna use this block in 3 places, which is 1 in encoder and 2 in a decoder. So the input of the multi-head self-attention are the query, key, and value. We need to have a projection. So after having a projection,
Chen, sorry, could you please go closer to the mic for the audio?
Okay. Can you hear me?
It's about the same as before. Could you just maybe be louder or closer?
It's louder.
Speak louder.
Or closer to the mic?
Closer. Okay.
Thank you.
So for multi-hot self-attention, the input is query key and value. After doing the projection, we then using the formula to have the output. And remember, we need to have a final linear layer after that. This is add a norm. Add a norm is to maintain a stable gradient flow. So it consists of two parts, just simply having a residual connection and a linear normalization like that. Then about the feed-forward block. Feed-forward block is just a simple MLP. We first have a linear layer and then add in ReLU activation dropout and then add another linear layer to that. So this is a feed-forward block. After having all of those four basic blocks, the positional encoding, multi-hat self-attention, add a norm, and feed forward, we can put them together and construct the encoder and decoder. For the encoder, following the paper, we first have a self-attention block, and then do the add a norm, add a feed forward, and then add another add a norm. For the decoder, we first have an attention, then add a normalization. Also another multi-hat self-attention, another multi-hat self-attention block, do another add a norm, and then feed forward and another normalization. So we have to pay attention that those two multi-hat self-attention blocks, we have different inputs to it. So for the first, we just put, so for the key value and query, like all of those three values are the input. But for the second one, we should pay attention that the key and value should be the output of the encoder layer. Okay, after we have the encoder and decoder, we need to construct the transformer. So for the transformer, we first have to do the embedding and the positional encoding for both of the source and target, which is in this translation task. We need to do the embedding and the positional encoding for both English tokens and German token. After that, we have a loop for the encoder layers. And then we have an output for the encoder layer and put it to the decoder layer together with the German, and then go through multiple decoder layers. In the end, we have another like linear layer to the output of the decoder layer. So then this is the output. For the training, there are multiple hyperparameters we can set. So for example, we can set the dimension of the model, the number of the attention heights, a number of layer for the encoder and decoder, for example. Yeah. And yeah, I think that's it for my part. Yeah, this is a model, and then we can do the training on it. Yeah, I think that's it. Thank you so much.
Actually, the notebook is runnable, so.
If you want to show them. Well, hopefully, I finished most of the material. And the reason we have this notebook here is because you can train it right here. Okay. Well, its download speed was. Oh, okay. Never mind. Oh yeah, I want to just know one thing. Remember that I told you that attention when training transformer, you just want to do a huge classification task. Well, the key is here, right? If you want to train your model on classification, you want the cross entropy loss. This is the proof of my argument. And if you look into the training loop, somewhere down here, you have this. You're flattening. Well, because it's a huge. Each is a batch of. It's a batch of sets of classification tasks. You're gonna flatten it and apply cross entropy loss. Pretty much. I think it makes. Hopefully, it makes it clear of what a transformer does. And I'm wondering why these libraries are stalling that slow. All right, we're finally installing all of them. Hopefully it's close. Here's the training loop. Actually, let's get started on the other notebook and let it train a bit. The previous notebook is on a pretty standard language to language task.
Oh,
Never mind.
which is pretty straightforward because language tends to. Wait, is it completely off? Hello?
Hello? Oh, better. Because languages are words that are stuff that are pretty. It looks like a sequence at first glance, right? But a more implicit application is how to apply it on vision tasks. Think about your homework 2 assignment. What you're gonna do is that you're given a class of people, several people, a lot of people, and for each class you're given some images of their faces, right? And you're gonna train a model that classifies a given face into the person. At first glance, the image does not look like a sequence in any form. But if you think of what a convolution layer is doing, it is taking little patches of the image, and then they're concatenating them into either it's 1D or 2D or 3D, an output of the same dimensions, same number of dimensions, but it might be with a different size. And if you really think of how you do the convolution in depth with the stride that is the same as the kernel size, then you're going to have an unoverlapping little patches being multiplied with the future. And this basically just breaks your image into smaller parts, right? And if you have a convolution layer that breaks your input image into smaller parts, then you have effectively converted them into a sequence. And because transformer is a sequence model, it's a model that takes sequence as inputs, and it can take sequence as output. But what it can also do is to add extra tokens in your output that serves as a different purpose. And in this example here, we're going to see what happens, right? And the first task is to apparently install these libraries. Okay, then we have to download these data sets. Okay, let me actually, which one? This one. Okay. The data set is what's called the Amnes data set. It contains 10 classes corresponding to the 10 digits. And for each class, it supplies a grayscale image of a handwritten digit with a black background and a white the white places corresponds to the digit itself. So it looks like this. Yeah, 08. I cannot recognize this. Maybe 7, 76469. This is a 7, something like this. And the task is apparently to classify which, given a handwritten digit, which actual digit does it corresponds to. Okay. So now this is the process I talked about, right? The way it is equivalent to having a convolutional layer with the same strides and the same filter size, and which converts your input into like 9 these little patches here. And if you order it, in some way it becomes a sequence. And this code is going to do the task. You can specify the number of patches you want on each dimension, and then it helps you like cut or crop your image into those small patches. If you look at this code carefully. Another way to do this is just to use a convolution layer, but the code here makes it more clear of what is going on when you're converting the image into patches. And this is the model architecture. This part is your input sequence. This part is a linear projection. It is something similar to in your homework tree. You're taking your MFCCs and you're mapping them into some dimensions, right? Because you're not operating only on the raw data. And it is a similar idea here. You're going to map the pixel values into some dimension as their embeddings. And which, as an analogy, in the natural language case, you have a tokenizer. These are like tokens, which actually doesn't make their index does not contain any information, any useful information. What you have to do is that you have to get an embedding for them, which is pretty much equivalent to a huge array. And in the case of images, the pixel values themselves makes a lot of sense, like contains all the information we need. So we are making a linear projection of them, something similar. And then after you've converted your input sequence of patches into some dimension, some space, some feature space, you get a sequence of features of vectors, and then you pass this through the transformer encoder, which is pretty much similar to what is proposed in intention of in the This is all you need paper. You have this multi-head self-attention. Then you have the skip connection. You do normalization, and then you go through a linear layer. And after that, you add a skip connection and do normalization, and you stack it several times. And what comes out is for each input token, their hidden state entangled with each other's information. And a key step here is that the author of this paper decided to add an extra token at the beginning of these patches to serve as a so-called classification token. Because if you look at, well, of course, this is not mask attention. Every token is going to learn information about each other, but the author somehow decided to add this extra token here And when it is passed through the attention layer or attention block, it is going to learn information of all the other patches. And hopefully, because it is not an image patch itself, it does not contain some potential bias that might be contained by the rest of the tokens that corresponds to the patches. And I think the intuition behind this is that if the token is a patch itself, then the information it learned might be kind of somewhat associated with only this portion that the patch is going to correspond to. But adding a token that is independent of the patches can sort of mitigate the problem. I don't think the authors talk about this in their paper. That's my personal thoughts. I think it makes sense. Yeah. So what happens after adding this extra token, and of course with the positional embedding? Oh yes, and this is in this case the positional embedding. This does not need to be very complicated. Instead of calculating the mass terms as we did for the transformer for natural language, what you can do here is that you can initialize another embedding, or just one embedding, and because for a given image of a fixed size, and given that you're dissecting the image into patches using the same fashion, you always have the same number of inputs. So for example, if you always have image inputs of size 224 by 224, and you're cropping your image into 14 by 14 patches, then you're always going to get I think you're always going to get 16 by 16 patches or something. Like the idea is, yes, the idea is that with a fixed image input size and the same way you're going to create a patches, you always have the same input sequence length. And so for positional embedding, you can initialize an embedding like a huge array that contains like a learnable vector that is hopefully going to encode the position information for each of the input places. And you just add them to the tokens in a usual way. And after you pass through the transformer encoder, you get a hidden representation for each token here. And if you kind of recall what happens in the decoder part of the transformer model, you have a linear classifier on top of each token. And in that case, it is predicting the next token here. And in our case here, we only need the classification head on top of the classification token to classify the class for us. And this is basically the architecture of the model. And oh yeah, for some reason this notebook decided to use the same positional embedding as the attention is all you need paper. But I believe in many applications people are using something. A lot of applications people are using fixed like learnable embeddings. Other embeddings include like rotary embeddings, which ensures that you have the same pairwise distance. But yeah. Okay, so this is the multi-head self-attention stuff. This should be exactly the same for any transformer, because after you've converted your input sequence into a sequence of hidden vectors, it is exactly the same in terms of the shape of the sequence and the model. So nothing fancy here. Usual attention block. Okay. And the VIT block here, you're passing through the attention layer, add a skip connection, pass through MLP and add a skip connection. Oh yeah, and of course you have to do normalization. So nothing fancy. This is the final attention class, final transformer class. So see that the output, this is our classification token. Added, let me see here. You initialize a class token as a learnable parameter, and you're gonna append it to the sequences here, just resembling the architecture shown in this graph. You are appending an extra token to the sequence of the image patches. And then you are going to pass this through a model with their positional encodings to get an output. And to do the classification, you only take the first token, which is, because the way it is concatenated is that it is concatenated to the front. So you take the zeros, and it passes through the classifier. to predict the class of the image. So that's basically what happens. And some hyperparameters. Small model, but the MNE is it's very easy task, so hopefully it's able to do it pretty well. Okay, so let's just let it train and we take a look at our previous notebooks results. Okay, the loss diminishes pretty fast. The blue score is a metric that that kind of measures the quality of generated text. There are many other metrics. You have blue. You have meteor. You have bleep. Well, there's a lot of scores out there, and I think blue score operates on the n-grams. N-grams means like n consecutive characters. It calculates some sophisticated functions of the n-grams, and what the takeaway is that with a higher blue score, you have a higher quality of generated text. And here are some examples of the generated stuff. It's doing English to German translation. So it's pretty powerful, right? I think. If you have, okay, I don't know how old are you, but if you have like 10 years, like 10 years earlier, the translation software is literally trash. It's like, for languages that are different enough, it's not going to perform very well. It's going to perform very bad, actually, to be specific. But now with this transformer model, we can train a decent model that translates English to German at a quality that is pretty decent. Yes. Okay, so this is all we have for the language notebook. It might be helpful to examine it in detail for homework 4, but I'll just, okay. And then now let's get back to our vision transformer. We finished training it. This is just a cross entropy loss. This is the test loop. We have 83% accuracy. That's pretty decent. And this is a example of some test cases. We have success cases. We have failure cases. Well, this is a weird failure case because it is a pretty clear 2. This is a pretty bad failure case. This is an interesting failure case. Like, I don't think anyone can really figure out that this is a 5. But yeah. And we have a 5 that is predicted in the 3, which kind of makes sense because 3 and 5 looks alike. Yeah. So I think this basically is all with vision transformers. I can recap on this architecture. I have an extra token here that does the classification task. Right. That's all we have for today, I believe. Do you have any questions? Oh, by the way, we are having the bootcamp for homework for tomorrow. So if you have been struggling on homework, then maybe try to make it to the bootcamp. We're gonna release videos, of course, of the recordings, but just as a reminder. Right, if there's no questions, I'm probably gonna say goodbye to you guys. Okay, see you.